Hi there, my name is Dr. Corey Clark, and I'm going to be giving a lecture today that's specifically focused on introducing clock and time synchronization. So, this is a really important topic because fundamentally, all our power stations, our internet, our financial systems all rely on highly accurate and precise time distributed throughout the entire world. So, that's what this first lecture is on. There will be a second lecture as well, which is more focused on specific standards that are used. But the key thing to take away from this lecture is to really get an understanding of the fundamentals. I will get mathematical at times, so bear with me, but nonetheless, it should be quite useful if you're interested in working in this area. So, without further ado, I will just switch over to my lecture slides. So, yes. And I would also like to quickly thank the Royal Academy of Engineering, who's provided support to enable me to make this lecture for you today through my research fellowship with the Academy. So, firstly, some fundamentals. What exactly is time synchronization? So, fundamentally, time synchronization is the calibration of the time, or we can denote this with the letter T, of some subordinate clock to match a master clock. So, for example, here's two examples here. So, we have some master clock that has the correct time. This is before we do any time synchronization. And we've got some subordinate time that hasn't had its time set at all, and it's set to the beginning of the Unix epoch. Unix epoch as it happens, of the 1st of January 1970. And then we have some time synchronization take place, and then this master clock sends through its time, and the subordinate clock ends up synchronized to this primary master clock. And this might require multiple transmissions. The master clock may need to transmit to the subordinate clock, and the subordinate may need to transmit back as well. We'll get into why you might require that later on. But a key thing is about all time synchronization, from someone telling someone else what the time on their watch is, to modern computer systems and the internet, where time synchronization is absolutely critical. There's always some imperfection and error that remains. In this case, this subordinate clock, even after some synchronization has been done, still has a 5 millisecond error on its time in comparison to the master clock. So, a highly related concept is that of synchronization of clocks, or clock frequency synchronization. And you can really break this down into two different components. So, firstly, we have clock frequency synchronization. So, this is matching the clock frequency, f, of some subordinate clock to a master clock. This is like, matching the rate of ticks on two watches, or two grandfather clocks, or whatever you like. So here's a handy diagram of this. So we have a master with one clock frequency, and then we've got a subordinate with a different clock frequency that doesn't match the master. You can see that these ticks are more compressed. And after we do some frequency synchronization, what we end up with is that the frequency of the master is the same as the subordinate, but not necessarily the same phase, which we now get into. So a phase is like the time at which the ticks happen. So then we have clock phase synchronization. So in this case, we're matching the clock phase, usually denoted by the symbol phi, of some subordinate clock to a master clock. And this is matching when exactly the ticks happen. So it's like you tune your watch so that when one ticks, the other one ticks at the same time. They're in unison with each other. And diagrammatically, you can represent this like this. Before synchronization, the master and the subordinate happen to have the same frequency, but they have a different phase. They're in a different position. The ticks happen at a different time point. But after we do some phase synchronization, then they match, which is great. Good. That's what that does. But an important point is that frequency and phase synchronization are directly related. So the clock frequency is the instantaneous derivative of the clock phase. You can see this in this diagram. So we've got a plot of the clock phase against time, and this isn't perfectly linear. There's some wandering because the frequency shifts over time. And if we find the differential of this curve, then what we end up with is the frequency through d phi divided by 2 pi dt. So then let's move on from that and get on to where do we actually get time from? Because, imagine you have a watch and it just sends out ticks. It doesn't really tell you anything. It does, in a sense, but it's not the same as, say, you being able to go up to someone and go, it's 12 o'clock. I.e., a clock without some source of time is really just an oscillator. To get a clock, you need an oscillator plus some massive counter. So they have a frequency. They have some degree of stability. You can see this in this plot, so you can see the edges are wandering a bit here. So it's d phi, or our uncertainty in the clock phase. So the key thing is that we need to source time from somewhere, and ultimately time comes from one of the national timing laboratories worldwide, and there are many of them. Most countries in the world have their own timing laboratory. For myself, living in the UK, my national timing laboratory in the UK is the National Physical Laboratory. And every single timing laboratory has its own timescale, which is usually denoted UTC bracket K close bracket. So if you synchronize to MPL's timescale, then you are sourcing time from UTC bracket MPL close bracket. And the key thing is that there isn't really a source of international atomic time that you can just casually tune to, but nonetheless, collaboratively, every single national timing laboratory across the world brings together all the measurements from their mostly cesium atomic clocks and hydrogen masers and decides on what international atomic time should be by averaging every single clock across the world. And then each of these UTCKs are all steered towards that point. So here's an example. You can actually set this in your home router if you so wish, like me, for instance, to bring a source of NTP, which is a way of delivering time over large-scale networks, to MPL. So you can lock, for instance, to ntp1.mpl.co.uk, and you can get your time directly from the cesium atomic clocks running in MPL in Teddington, just towards west of London. And typically in many web networks they will take this source of time and use it to synchronize a grandmaster time server of some description, which will usually have an atomic clock attached to it, mostly because if the system goes down, you've still got the atomic clock there to give you a good estimate of what true time is. So why does this matter in a data center concept? So both of these lectures are going to mostly be focused on data centers, as the module that I taught at my university. This was originally its target, so this is what this is around. But nonetheless, data centers are probably one of the main markets of time synchronization. So the key thing is that if you have services running on servers across a cloud data center, if they have the incorrect time, it could lead to poor performance between services within the data center or to services outside the data center, and it could even lead to errors or lost data in some cases. So a great example, I think, is a massive transformer model. So say like ChatGPT-4, very current. So in ChatGPT-4 there's approximately 1.8 trillion parameters, and if each parameter is one float or 4 bytes, then you end up with about 7.2 terabytes of total values. And these are much too big to store in one GPU. So one of the biggest GPUs you can get now, which is really targeted specifically for big neural networks in cloud data centers and other places, is the NVIDIA A100 with 80 gigabytes of VRAM. So in order to run this model, you've got to spread it out amongst all these GPUs. And that means really over 90 network GPUs together. And the data sent between GPUs in each of these model layers needs to be coordinated somehow. So for instance, here we've got a deep learning network and we've got some hidden layers, and we've got our input parameters coming in on the outside, and some of these parameters are going to be stored on some GPUs and some on others. So this is a really simplified version where we have just a couple of parameters spread across 4 GPUs. But the key thing is we've got all-to-all communication here. Everything is communicating to everything else. So you've got a lot of communication coming on, and the key thing is that data sent between GPUs in each module layer needs to be coordinated. You can't be randomly sending out new data packets to different places. You've got to keep everything running on the same time. So we need time synchronization to keep the calculation coherent. And we also need, ideally, to stagger the data transmissions between the module layers so we don't suddenly spike out the load. So you could end up with something like this, where all of a sudden your load spikes through the roof, goes over capacity of your network before dropping again, and then does the same at later stages. But if you have time synchronization, then you can stagger these out, so you spread out your load and things are much better. But there are lots of data centers that aren't just running transformer neural networks, right? There's a lot of different things. So many data centers handle time critical data. So, for instance, consider a mobile network provider's data center. So, for instance, EE in the UK. So they are handling mobile traffic from base stations. And here, timing is absolutely critical. If you have inaccurate synchronization, it leads to issues handing over transmissions between different base stations. You need to tell a device when to stop transmitting to one base station and when to start transmitting to the other, and vice versa. You have issues potentially with poor spectral efficiency as well, if you can't have very accurate synchronization. And on standards, when we look at those, so because of this, at least for 5G, all front haul network base stations need to be synchronized to within 1.5 microseconds of some central time reference in the network. And these requirements are likely to get even more tight in 6G. Another great example is finance. Timing is absolutely critical. Many data centers run in, say, City of London to deal with various timing transactions, and if you have inaccurate timing timestamps on transactions, it leads to doubt. It makes it unclear which trade might have been first if the timestamps are close, and that can be a real problem. You get uncertainty over who went for the stock first, and in certain cases, if the inaccuracy is bad enough, you don't know. For this reason, it's regulated by both EU and US law. You can look these up, the MIFID2 and the CAT, respectively. And both of these standards state that all financial transactions must be time-stamped with, firstly, an accuracy of within 100 microseconds of UTC. That means they need to be within 100 microseconds of absolute time, i.e. to MPL in the UK, or to NIST if it's a financial centre in the US, for instance, and the precision of those timestamps, i.e. the difference between the timestamps within the data centre itself that's running these financial transactions, need to be within 1 microsecond. So another very important application for time synchronization. So then the question is one of what sort of accuracies do you need? So in older data centers, say early ones run by Facebook, they required millisecond accuracies, and you can do that with standards such as the Simple Network Time Protocol, SNTP, or its superset protocol, the Network Time Protocol, or NTP, which are both probably some of the most commonly heard of protocols today. We'll cover these in the second lecture, which if you watch both of those today will be later today. And for millisecond accuracies, you can do the time synchronization purely in software. You can have a CPU dealing with it. You don't need to do any more advanced tricks. However, for modern data centers, particularly those that run really demanding applications like transformer neural networks or handling mobile traffic, they really require sub-microsecond or even nanosecond accuracies. And that can be done with the Precision Time Protocol, or PTP, and I will cover that in some detail, quite a lot of detail actually, in the second of the 2 lectures I'm recording today. But the key thing is to be able to do synchronization to sub-microsecond or nanosecond, you need to do the synchronization in hardware itself. You can't afford to have the inaccuracy that's caused by simple time to get through queues that happen to be in software. You have to do it at the hardware level away from the CPU. So we'll explore that a bit later. So then another really important question is, I say time synchronization error, and I say that it's critical. But it's important to recognise that there are two overarching types. So the first is accuracy. So this is the mean error of the subordinate clock from the absolute true time. This is often also called the time offset. The second part is precision. This is how much the subordinate clock's time error varies. We also can call this time stability. And the two terms in base English are often used synonymously, but strictly speaking they're not quite the same thing. And the best way to illustrate this is, as always, with a bullseye. So here we have effectively a matrix of not precise and precise, as well as not accurate and accurate. If you imagine an archer, so if they're a really terrible archer, they just sort of shoot randomly at the target, and there are a load of arrows which are sort of all over the place. And their mean distribution is not in the centre of the target, they're sort of away from the target instead. If they were precise, i.e. very, very good at consistently hitting the target in the same place, but not at the bullseye, we would call that precise, but not accurate. If it was accurate, they'd be at the bullseye, right? If, on the other hand, they're pretty good at shooting at the target, but they just have this general distribution around the centre, we might call that accurate, but not precise. But what you really want is you're an archer that consistently hits the bullseye one time after another, right in the centre, with very, very small spread around that point. And that's what you want in time synchronization, and in many applications. You want accuracy and precision. So, then the next topic is noise. And this will at times get quite mathematical, because I will dive into some of the common metrics which are used to quantify clocks and time. So, in many aspects of electronic engineering and physics, lots of types of noise can be modelled as Gaussian. Gaussian noise is lovely. It's lovely because it follows a normal distribution, which we also often call random noise, which has a power spectral density, which is effectively the noise in the frequency domain squared, divided by some frequency bin. We'll see it shortly. It's constant, so if you plot it against frequency, it's just flat. So a really good example is called thermal noise. You see this in fundamentally all electronic components, and it's modelled as VRMS, so root mean squared, squared, so effectively this is the variance, is equal to 4 times Boltzmann's constant times the temperature in Kelvin, not in degrees C, times the resistance times by the bandwidth, or delta F, so i.e. the frequency range over which we're looking at. So this is why it has a constant power spectral density, because it's literally just linear in V squared with delta F, the bandwidth. So for random noise, standard deviation is an excellent measure of precision. And the reason for this is it doesn't matter for how long you measure, as long as your measurement bandwidth doesn't change, your standard deviation is not going to change, because your measurement time doesn't affect the noise magnitude, as long as you don't divide by the number of samples, right? So if you were to measure for, say, 10 seconds, you'd measure the same amount of noise, the same distribution as you would if you measured for an hour. But a key thing is, are long-term sources of noise also random? So by this I mean changes in oscillator clock frequency caused by temperature and voltage shift in particular. So say, take your watch, so typical watch, the rate at which these ticks slow up and slow down and speed up is not Gaussian. You can't model it in that way. You need a different way of doing so. So what this means from the perspective of calculation and measurement of noise is that the oscillator frequency fluctuations over seconds, hours, days, etc. are not random. Standard deviation increases typically the longer you measure for. So you have to use different metrics to quantify the precision instead. The first of these is a metric that is commonly quite hard for people to understand. In fact, most of these metrics are, because they're not Gaussian really. So if you want to quantify noise that's on the short to medium term, so by this we mean under a second, so noise that's got a characteristic frequency of under 1 Hertz. Typically you use the clock phase noise, alternatively just called the phase noise. And this is the noise relative to the carrier frequency. So i.e. if you have a clock that ticks at say 800 megahertz, then that is the carrier. The fundamental carrier in that system is 800 megahertz. So this is the noise relative to that carrier at some frequency offset, delta F, measured within a 1 Hertz bandwidth. So here we have the power spectral density. So this is given by the Fourier transform of the clock in the time domain. So you imagine you'll have some sort of sinusoidal fluctuation, right? And that will have some phase error on top of it. That will be moving about as a function of time. And you do a Fourier transform of that. And if you're not familiar with a Fourier transform, all it pretty much does is it takes that time domain signal and turns it into frequency against power. So you have frequency on the x-axis, and in the y-axis you have not power but the Fourier transform. But if you square it, then you end up with power after you normalise by the frequency sample size in question that you use in that Fourier transform. So this is what you end up getting. So this is our carrier frequency, so say this was 800 Hertz for instance, and it's not perfect. If it was an absolutely perfect clock, it would be a straight line here sticking out from the surrounding noise. And what we do here is we take some single sign bad measurement, which means that we take a positive offset from the carrier. By definition, this is what we do. And we measure the amount of noise in a 1 dB bandwidth that's down from the carrier frequency. So for instance, say this level of noise was 100 dB lower at this point, we would quantify the phase noise at this offset. Say it was like 1 megahertz as minus 100 dB, because this ends up being, this will always be negative because the carrier will always be greater than the noise. This will never be inverted, right? Your noise will always be at a lower power spectral density. So what you end up typically seeing is that the further away from the carrier you get, the lower and more negative phase noise. So for instance, if you're very, very far from a carrier, you'll notice the waveform becomes, not the waveform, the power for spectral density becomes flat. And so we see that here. This is effectively our Gaussian white noise right at the edge. This is typically on megahertz order. And then as we get closer and closer to the carrier, then our phase noise increases until eventually right at the carrier we end up at 0 dB, if we can get that close. So obviously the closer you get to the carrier, the more difficult it is to measure. So that is phase noise. What you usually see is that as the frequency offset increases, the phase noise decreases. Sorry, I should say decreases. I'll correct that in the PDF. So then you can look at the various types of noise that you find in the phase noise. So A really important thing to note is that you notice there is a flat portion here. So this is white phase modulation. So this is white noise. This is the only part which is actually Gaussian possible to model. That's typically in megahertz frequency ranges. So this really tells us that standard deviation over pretty much all frequency ranges is a really poor metric for measuring clock error. You need something better like phase noise or like the other metrics we're going to go through. And as you decrease in frequency, what you almost always see is the contribution of other types of noise. So with a proportional to about 1 over f is a flicker phase modulation contribution. When we've got 1 over f squared, which is the white frequency modulation. When we've got a 1 over f cubed, which is our flicker frequency modulation. Then finally we've got random walk with 1 over f4. And if you measure to a really low frequency, which typically you won't with phase noise, when you start seeing frequency drift as well. But we usually use other metrics. So you see typically a cutoff of this. You could go down to 1 hertz, but more typically you'll see people going down to about a kilohertz, usually. So these are the types of noise that you might see. So then we're going to other metrics. So when we're looking at clocks over a long period of time, we really move away from phase noise and we start using other methods. So the first of these, the simplest, is the time error. So this is a difference in time between two clocks as a function of time, between say some master and subordinate clock. And it's very much like, two people comparing their watches over the course of a few days. Like maybe one is faster than the other. That's all this is. And you can see this in this plot. So you've got time on the x-axis. You've got time error on the y-axis. And over time, the time error is changing due to some clock drift that's occurring. And you'll notice a mean time error indicates the time offset or the accuracy of the system you're using. There is another way of looking at this as well. So you can also look at this as time interval error. So this is the difference in time between two clocks as a function of time that has accumulated since the beginning of some measurement. So say you and a friend set both of your clocks equal to midnight one day, and after a month you compare to see where they are, do the same after another month, etc. That would give you a time interval error measurement. The difference between them would be exactly that. So you can get this mathematically simply by taking the time error and taking away the time error at time 0. So this is the same plot as t, just moved up really. That's pretty much all that is. So then we get on to a metric that you often see in standards. So this is the maximum time interval error, or TI. And this quantifies the largest variation of the time interval error, or TI, measured between two clocks in some observation window of length, tau. And you sweep that through all the recorded TI values. And a key thing to bear in mind is tau is equal to n, always some integer, times tau 0. And this is effectively your smallest possible observation window length. Usually, tau 0 will be equal to 1 over fs, where fs is the TI sampling frequency. So here it is mathematically. So you've got the, you find the maximum of the TI as you sweep through this set of observation windows value. You find the minimum that you see within this observation value range, and then you're sweeping that entire thing through the entire data set, and that ends up giving you the maximum at that observation window length. And then you make your observation window length bigger and you sweep that through, you make it bigger still, you sweep that through, etc. And eventually what you end up seeing is that the longer you make that observation window that you sweep through your data, the bigger the peak-to-peak variation that you see in that data set. So the result of this is that MTI always increases with increasing tau. Doesn't matter what the clock is, this is always the case simply by how the measurement is defined. And this is a really key metric in standards. So for instance, there are typically standardized limits on MTI for a given class of clock. So for instance, PRTC class A clock and there's a limit of 100 nanoseconds MTI after I think about 100, about maybe 200 hours. I can't remember exactly what amount, but if for a clock to fall within this class, it needs to have an MTI that's below this threshold, and if it doesn't pass this, then it operates out of spec. So that's the first thing. And what you also typically see in this is that the requirement on MTI is tight at the beginning, say 20 nanoseconds for this particular class, and it will rise to a higher value. And these amounts of times can be quite long, so it can be as long as specified for 3.2 years, for instance. So then we have a metric which often causes confusion, because it is a relatively complex metric, but it can be broken down in such a way that it's actually not hard to understand, I believe. So both Allen variance and Allen deviation quantify the stability of the fractional frequency difference between two clocks. So i.e., if you compare two clocks, how much one of those clocks runs faster or slower than another over some characteristic timescale. And just as with the MTI, we've got some windowing function which we're sweeping through, so we're sweeping this all the way through a data set. And just as before, we have tau 0, where that's usually 1 over the sampling frequency of that particular data set, and we have tau once we multiply that by some integer. And you can see our data set here, that's a tau, and we have some observation window length, and this time the observation window is 2 tau. And what we end up doing up here in this sum is we add the two outer values, so the one at ti, and then we add ti plus 2 tau, which is at the other side of the observation window, and then we take away twice the value that's right in the middle. And so if I demonstrate that for, say, sweeping through like the first, second and third, and then moving that onwards in terms of the actual values in the tie. So for instance, we start with our observation window at the first sample, we add the third sample, and we take away twice the middle sample, and we then sweep it through, and then we go to the next point and we do the second plus the fourth minus twice the third, and then we move on and do the same until we've gone through the entire data set. And each of these additions and subtractions we square, and then you do some normalization as well. So once you've got the entire set of observation window positions, you then divide by capital N, which is the overall number of samples, minus 2n, which is the integer you're using in the calculation for tau, and then you've got a conversion for frequency as well, so this is n squared times tau 0 squared, and then finally we have a little factor of 2 here, so that's to account for the fact that we've got two differences here that we're needing to find essentially the average of at each characteristic observation window. And then finally, I mentioned that we have Allen deviation, so this gives us the Allen variance, but then if we want the Allen deviation, all we need to do is just find the square root. So what we end up plotting is actually quite interesting. So we don't plot t. We're not plotting the data set as a function of time. We're plotting a data set as a function of this observation window, tau. And so what we're seeing is the amount of noise that's measured over each characteristic length of time. So what you usually see is if you measure over a short period of time, the noise is mostly Gaussian in nature. So you end up with this falling off with some characteristic frequency. And then what ends up happening is that increasingly other sources of noise, which are non-Gaussian, start to appear in your fractional frequency difference. And this causes the stability to degrade as you go to larger and larger tau. Almost always this is plotted log-log, and the values can end up getting very large in some cases. So you might end up measuring for characteristic times of potentially 10,000 seconds or more. You can go for much longer, but at this point it starts to get far too long to actually take the measurement. An important thing finally to note is that this is all unitless. There are no units involved in this. There are in some other metrics, but not in this one. So then we have a highly related metric, and this is called the modified Allen variance and the modified Allen deviation. Sorry, just having some tea. And this is an extension of Allen variation and Allen deviation to separate white phase noise from white flicker phase modulation. So a few things have changed here. So we have an extra sum that's kind of on the inside, and we've got an extra n squared value here. And what these two things together are doing is they're averaging over some bandwidth n squared. So we're effectively adding a filter of variable bandwidth to this calculation. And this changes slightly as well, the number of observation window positions. So that's just some normalization needs to change because we're not taking as many different window positions. But what we're fundamentally doing on the inside is the same. We're still taking two values at the outer edges of this observation window and taking away twice the middle values. The resulting calculation that you get is still unitless. So once again, the modified Allen deviation ends up being the square root of the modified Allen variance. But what's changed is that now the flicker phase noise has got a different slope to the white phase noise, and you see this in this little knee here. Again, you usually plot this log-log, and usually you have degradation of stability at large tau. So the reason really that I've introduced this particular metric is because it leads directly to this one. So the time variance and the time deviation, TVAR and TDEV. And these quantify the stability of the fractional time difference between two clocks. And they're calculated by scaling this MVAR, MVET, sorry, that's my dog, MVAR, MDEV into the time domain. We've got the same function for tau, we have the same observation window lengths. But then what we're doing is we're multiplying by n squared tau 0 squared, or equivalently multiplying by tau squared. And we're also dividing by 3. What this does is it ends up normalising TVAR to be the same as classical variance, as long as the deviations in the time interval error are random. So what that means is if the entire noise fluctuation as a function of time was Gaussian, then you'd end up with exactly the same result out of the TVAR as the just running a standard deviation on the entire data set. So this is a great metric because I find it very hard to understand the concept of frequency variation. Like if I was to say to you that a clock runs 1 parts per million fast than another, it would be very difficult to get your head around what exactly that meant. But if I was to tell you that one clock fluctuates by about a second over the course of, say, a month, you'd have a lot more idea what exactly I was talking about. It's much more real. So I think this really is why it's used heavily as a key metric in standards. So, for instance, you see standardized limits on time deviation for some standard of clock, just the same as MTICE. So you might typically see, say, on a PRTC Class A clock, you might see that within a period of 100 seconds, it needs to have stability of within a nanosecond. And stability is really precision in this sense. But then after about 150, I think after about 200 seconds, then this needs to be within a much larger amount of 30 nanoseconds. And as long as the clock shows a TDEV of below this, then it passes that particular specification. And just in case I didn't say, the time deviation is simply the square root of the time variance. And again, this is usually plotted log-log. Not always, but usually is. So I think the other important thing is that the noise types that you see in the phase noise, you also see here. So different types of noise scale with tau in the time variance, just the same way as with frequency you get scaling of the phase noise. And this is also true in both the Allen and the modified Allen variances too. So for instance, the time variance, or TVAR, tau of capital N, we see white phase modulation with characteristic frequency of 1 over tau. We've got our flicker phase, which is constant as it happens in the time variance. Then you've got your white frequency modulation. This scales with about proportional to tau. Then you've got flicker frequency modulation. This is tau squared. Then you've got random walk frequency modulation. This is proportional to about tau cubed. And then finally you've got your frequency drift, which is proportional to about tau to the power of 4 or more, potentially, depends on your type of drift. The key thing is that the sort of timescales that the first 3 of these are measured over, you're not typically going to plot with time deviation. You might, but you probably won't. Typically the cutoff is on the order of a second or so. Usually you'll use the phase noise for these shorter term ones. Typically you'll start time variance at 0.1 seconds or 1 second. So then we're moving on to metrics, and from this point the presentation gets a lot easier to digest, I think. So this is more purely focused on how we actually do time synchronization. So there's a really simple way you can do this for starters, and that's called one-way time synchronization, which is much like setting a watch. So the idea is that your master clock sends some timestamp, which is really a packet that has some recorded time value. Like it could be 1 minute past 12 on 7th of January 1970, for instance. And the master clock sends that timestamp with the time to the subordinate clock. So we've got that here, master sending to the subordinate. You could send that data packet using Ethernet or some other protocol. You could send it through optical fibre. You could send it through coax or twisted pair cable, which you'll typically find, say, in a house, for instance. Or you might even send it wirelessly. And the way it operates is really like this. So on the master clock, when the master wants to send out its time, it reads its current time and it transmits it as a timestamp to the subordinate in some manner. A packet then flies through the wire or the cable or the fibre or wirelessly or whatever, containing that timestamp T1. You have some delay in the transmission medium. We're going to ignore that for now. And then the timestamp packet arrives at the subordinate, and the subordinate clock records the time of arrival of the packet on its clock, and it calculates the offset. So the offset is approximately equal to T2 minus T1 minus the delay between them. However, in this particular way of synchronization, we assume that this delay is actually nothing, that there is no delay. And then using this, so effectively you're doing T2 minus T1, no compensating for delay. The subordinate clock then uses the offset to shift its time accordingly. So it's like, I've got my watch and it says 2 p.m. and I tell my friend it's currently 2 p.m. on my watch, and he checks his clock and it says his is 1 p.m. So his offset is 1 hour. So what he does is he shifts his clock by 1 hour to as closely match mine as possible. But the thing is, for that sort of situation, it's not a problem, right? Because distance is really short, speed of sound is fast enough on human timescales. If my watch is a second fast because it's taken me time to communicate that measurement, you don't care. But in computer systems, this can create a massive flaw. That is that the accuracy fundamentally is limited by the delay during which the packet containing that time travels between the master and the subordinate, because that's not accounted for with this method. So there are many contributors to this. The first is the transmission medium. So for speed of sound, not that we usually communicate time through speed of sound over large distances, is about 300 meters per second, if I recall correctly. Um, but the bigger one is the speed of light in vacuum. So that's 300 meters per second, or equivalently, it's about 3 nanoseconds per meter. So that's a billionth of a second specifically. If you're using silica optical fibre or you're using coax, which is typical for pretty much all communication worldwide, that will change to about 5 nanoseconds per metre. That can add up. So for a data centre that might have a longest distance of say 2 kilometres, that can mean 10 microseconds of delay. If you're going intercontinental, say you're going from the UK to Japan, and in the very best case, if you go as the crow flies, that's 10,000 kilometres. That's huge. It's 50 milliseconds. And those aren't the only contributors either. So you have hardware, and through SERDES or serial transceivers as we call them, and hardware queues, you might get up to 100 nanoseconds of delay potentially, so 100 billionths of a second. And then if you're using a software protocol like NTP, you've also got the delay through the software buffers or queues, and that can be a few milliseconds, so also quite a lot. So clearly you have to have a better approach than this, because in big systems, especially going a long distance, you need to account for the fact that we have this delay. So this is a way you can do this. So this is the better approach. So you calculate and you compensate for the delay that happens in the offset. And so to do this, you do what's called two-way synchronization, which is where we have timestamps that travel in both directions. And so this is how this looks. So what happens is the master reads its current time and it timestamps that as T1, and it sends a timestamp T1 to the subordinate. And one thing to note, this is more important later on, but it may be that the master can't insert that T1 into the outgoing message. And so as a consequence of that, what it might need to do is to record the outgoing of this first packet, and then send that timestamp that's recorded as that packet leaves the transmitter within its circuitry, and it will then need to send that timestamp separately in what's called a follow-up packet. The subordinate has this first synchronization packet arrive, and as it arrives at its receiver, it logs that as T2 on its clock, and it also takes out that timestamp it receives in that packet and records T1 as well. There's a delay associated with the time taken to send this packet from the master to the subordinate, and let's call that DMS. The next thing that happens is the subordinate sends a packet to the master, and it records the time of transmission on its clock as T3. It doesn't need to worry about sending through some follow-up packet, because it doesn't need to send T3 to T4. All the calculation is going to be done here on the subordinate clock side, so we don't need to worry about that. But when this packet arrives at the master clock, the master records the time of arrival, T4, of that packet from the subordinate on its clock. And then finally, the master needs to get this packet with a packet with this timestamp T4 back to the subordinate. So it does this with this final transmission, and the subordinate then receives T4 and then does the calculation. And the key thing is, how do we do the calculation? So this is how. So how do we measure this delay between the clocks so we can include this in this calculation? So you can represent the offset in two ways. So you can represent the offset as T2 minus T1 minus the delay between the two clocks. So effectively it's as if T1 was transmitted later, right? And you can also equivalently represent it as T4 minus T3 minus the delay from the subordinate to the master. And we've got a reverse sign here, we've got a negative, we've flipped this around. We've done this because the comparison is in the opposite direction. So instead of comparing instead of seeing how far ahead or behind the subordinate is from the master, effectively what this would measure directly is how far behind the subordinate, how far behind the master clock is from the subordinate. So we flip the sign there. So then what you do is you assume that these two delays are equal, and we have to do that because we can't independently measure the delays. And it's the special theory of relativity, funnily enough, actually prohibits this. The two postulates are one that you can't independently measure the speed of you can't independently measure the difference between two clocks before synchronizing them, firstly, and the second one is that the speed of light is postulated to be the same in all reference frames, i.e. in every single direction it's the same. So what we end up doing is we assume that it's the same in both directions, so we divide all of this by 2. So effectively we're setting this equation equal to this equation, then rearranging for d, and then we're dividing the lot by 2 in order to remove this twice d contribution. And the offset calculation for working out for correcting the subordinate clock is the same as it was before, except that now we know d. So that is used whenever the subordinate wants to adapt its clock. And a really key thing is that the actual degree to which the two delays, the delay from the master to the subordinate and the delay from the subordinate to the master, are equal, is key to the accuracy or time offset of every single time synchronization protocol out there. And this difference fundamentally is called asymmetry, because the degree to which these two paths are the same is how symmetrical they are. So the opposite of that is asymmetry. So that's that. Then lastly, an interesting thing which can be missed sometimes is that actually you can use timestamps to synchronize frequency as well. So in time synchronized systems, real clocks drift in frequency over time. So some example causes include process voltage and temperature variation. So take a typical quartz oscillator. It might have been produced slightly differently. The crystal inside that might have been cut a slightly different way, so it might have a slightly different characteristic frequency. If you subject that crystal to a slightly different voltage, it might resonate at a slightly different frequency. And also, very common for say a quartz watch on your wristwatch, the frequency is at a peak at about 25 degrees C, so i.e. the temperature that it will sit if it's on your arm. If it varies from that, the frequency will fall. So together, PVT is a driver of differences in frequency. So how can we actually calculate the frequency offset using timestamps then? So for a subordinate to calculate its frequency offset or drift from a master clock, the master sends 2 packets, each containing some timestamp from the master. So we've got T1 and T2 prime. And the subordinate records these packets, arriving as T2 and T2 prime. And by recording these times of arrival, the subordinate can estimate the drift, which is used to align the frequency of its clock to that master's clock frequency. Essentially, it's a fractional difference you're measuring here. So you're doing the difference between these 2 timestamps and the difference between these 2 timestamps. You find the difference between the 2 of those, and then you divide by the difference between these 2 timestamps, and that's giving you a fractional frequency difference. So, for instance, if this subordinate clock was running really quickly, it would have a bigger difference between these 2 timestamps as these 2 packets arrive than the master clock. And so that would appear in this drift calculation. And the subordinate will use these values to correct its frequency over time. It will essentially feed that into its own quartz oscillator or whatever and say you need to run faster or slower to be at the correct amount. So yeah, that's how you can use timestamps to correct frequency. So that's very much doable. So that is the end of the first lecture. And so just to conclude, so in this lecture we went through what time synchronization is, which fundamentally it's matching the time of some subordinate clock to some master clock. We explored the sources of absolute time, and we explored how we determine absolute time. We explored why you should care. We explored why time synchronization to microsecond or even nanosecond accuracy is important for operating modern data centers. And we learnt to quantify error in time synchronization between two clocks, building up to the two common metrics in time sync standards, which are the maximum time interval error, or MTI, which is a key metric in time sync standards to quantify peak-to-peak time error against observation length. And we quantified the time deviation, or TDEV, which is a key metric in time sync standards to quantify the stability of the time difference against observation length. And we also explored, and this will be important for the next lecture, how time and frequency is synchronized in networks using single-way timestamping and two-way timestamping. And that is the end of this first lecture. Thank you for listening, and the second lecture will be more focused on different types of oscillator and clocks which you might see used in networks, as well as the different synchronization standards that we commonly use. And a big focus of the lecture will be on the precision time protocol, which is arguably the best, very, very commonly used commercial time synchronization standard.